Okay, our last example in this set of notes, example 10, sketch the graph of this rational function. Again, taking a look at the domain. The nice thing about this one is the denominator never equals 0, so f is continuous because it's the quotient of continuous functions. Or you could basically say it's a rational function which is continuous on its domain. So the domain is negative infinity to infinity, so we're good for that. Unfortunately, again, we have that situation where the degree on the top is one more than the degree on the bottom. So I know that I have a slant asymptote. So while we have no discontinuities, we do have a slant asymptote for our end behavior. I can determine the quick end behavior by doing survival of the fastest, which is x cubed over x squared, again, over x, or when it simplifies down to x. So that is going to be infinity on the right side, and on the left side, it's going to be negative infinity because of survival of the fastest. However, because we have a slant asymptote, I do want to go ahead and see what it is. Unfortunately, I think this one is also going to end up being x, but this is because I chose bad examples here. But when you divide this in, x squared goes into x cubed, x times x cubed plus 1 or plus x. And then when you subtract, you get your minus x down here, but this is a smaller degree than that, so technically it's plus 0. I do want you to realize that that does not always happen. I just happened to pick two that happen to have that slant asymptote of y equals x. So when we sketch it, we'll throw that in. Let's find our derivative, f prime of x. So low d high minus high d low 2x all over low squared, x squared plus 1 squared. Let's simplify really quick. We can pull out an x very easily. That's going to leave us with 3x cubed plus 3x. And then minus over here, I took the x out, 2x cubed over x plus 1 squared, which is going to give me x and x cubed plus 3x over x plus 1 squared. And that does factor, but I'll go ahead and factor it when I say f prime equals 0 for x equal to, be careful. See, I made a mistake right there, but your x squared plus 1. So it equals 0 for x equal to 0. If I factor this out, it would actually be x squared, and this would be x squared plus 3. X squared plus 3 doesn't equal 0, so the only critical value is for 0. So we can run a quick test. If you prefer this as x squared, x plus 3, for that top part right there, because you can see that the bottom is always positive, x squared is always positive, so the only place where it's going to change, that should be x squared plus 3. And that's always positive, so it never changes sign, so it's plus and plus. And so what we see is that we have increasing and then we have increasing. So they're actually, even though there is a horizontal tangent line at 0, there is not going to be an extrema there. So there is no relative max or mins on this graph because f prime never switches signs. All right, so that's number one. So now we'll come down here and we'll find our second derivative. Let's write down what f prime of x is so I have it handy. And I'm going to go ahead and multiply this out because I want to be the easiest derivative. So it would be x to the fourth plus 3x squared over x squared plus 1 squared. And I'm going to use that to find my second derivative. It's all about making choices. So low d high, which would be 4x cubed plus 6x, minus high, x to the fourth plus 3x squared, d low, 2x squared plus 1 times 2x, all over the bottom squared, squared plus 1 squared. All right, and the only thing is when you have this in this factored form, watch for your factors. I can take out an x squared plus 1, okay? Because this factors to, I can pull a 2x out, and this would be 2x squared plus 3, just kind of showing you. So there's a 2x that we can pull out. And here, let's see, if I pull out an x squared, this is x squared plus 3. And I don't see any more that I can pull out. So I'm going to pull out the 2x, x squared plus 1. So I have 1x squared plus 1 left. I pulled the 2x out, and I have this 2x squared plus 3 left. Minus, over here, we took the 2x, the x squared plus 1. So I have this 2x to the fourth plus 3x squared left, all over x squared plus 1 squared. And like I said, it's the algebra that kills you in this. It just gets kind of tedious. Let's bring those. Let's combine this one and this one. So x squared plus 1. And then in here, I'm just going to have to multiply everything out and collect like terms. So 2x to the fourth plus 2x squared. That's this one and this one. And then we need to do 3x squared and that one plus 3 minus 2x to the fourth minus 6x squared. And then let's combine like terms on that. Let's see. Oh, 2x to the fourth. It's always nice when things like that happen. 2x squared plus 3x squared is 5 minus 6. So that's minus 3 minus x squared. So all of that work, and it actually simplifies down pretty nicely when we're looking at it. All right, so our possible points of inflection when the second derivative is 0 would be x equal to 0 and x equal to plus or minus square root of 3. That's from the top. The bottom never equals 0, so we don't have to worry about that. We can do our sign charts. So negative square root of 3, 0 square root of 3, f double prime f, 0, 0, 0. And check our signs. The bottom's always positive, so we can ignore it. If I do a negative 100, that's negative. This would be negative, so two negatives make a positive. We'll check real quick. And then over here on this end, if I pick like positive 100, positive, negative, so that would be negative. If I check in between here, square root of 3 is bigger than 1. So like say I pick negative 1, that would be negative. This would be positive, so negative. And if I pick 1, positive, positive, positive. So we are concave up, down, up, and down. So we have points of inflection at x equals negative square root of 3 plus or minus and x equal to 0 because your second derivative switched signs. So when we sketch this, we basically have a function that is always increasing, that has a horizontal tangent line at 0 and has points of inflection and switches concavity 3 times. All right, so let's take a look at our graph, and we'll just let Desmos show us that all our behavior is alike. So let's come over to here. Curve sketching example 10. All right, well, I have it on here, but notice here's my slant asymptote. Here is my 3 points of inflection, and then I'm going to increase, and this is where you just have to be. Now look, when you actually look at this, it's not very clear that that's concave up. And this is partly why you need calculus and you can't go by, hey, it looks like it's concave up and concave down over here, what you're going to see is that it's actually going to be concave up on this section right here, and then down, and then up, and then down again. You're just not going to see the very slight curve that's happening right here. All right, so that should end up our example that we have for example 10. Now, you do have also in this set of notes, I believe I can go to the next page. Let's see, here and then here. In the curve sketching summary notes that are attached to this, you do want to go through this and take a look at it. This talks about what do we know if the shape of the graph looks, if it's decreasing in concave down, what do we know about our derivatives? Here's increasing in concave down. So this is just like a little summary when you're looking at it to kind of give you what do you know about the derivatives about these types. This section would be decreasing but concave up. This side is increasing but concave up as well. So you can kind of look at that and take a look at what's going on with your derivatives. Also, take a look down here. Here's your definition of critical values. Your function has to be defined there. That's the continuity part. And then your derivative 0 or does not exist. These are your horizontal tangent lines. These are either your cusp or your vertical tangent lines. So that gives you your critical values, places where that you may have an extrema. Your increasing, decreasing test, if your derivative is positive or negative and your function increases and decreases. Your possible inflection values come from where your function must be defined, and your second derivative equals 0 or does not exist. And I do want you to say also here, and f prime of c is defined, because you have to, well, maybe let's not say defined. Let's say, and f has a tangent line. F has a tangent line, because it can be a vertical tangent line and still be a point of inflection. You just can't be a cusp and a point of inflection. So if you have a tangent line, which means that you could have f prime undefined if you had a vertical tangent line. Your concavity test using your second derivative, and then if we look over into the next page, your first derivative test for relative extrema, local argument, your second derivative test for relative extrema, where you're looking at your concavity around that extrema so that you know what's going on. A point of inflection test, how do we know if it's a point of inflection? Your second derivative switches signs. And then this, I kind of alluded to this in one of the examples, and we'll talk about it here. This is your modified first and second derivative test, where we're modifying it for global extrema to say that it's the absolutely the highest or the lowest. So we saw one where I modified the first derivative, where I said that it was the derivative was always positive for everything before the critical value and always negative after. Then you know that it only goes up and then it comes down, and so it's therefore the only max that's there, so it's going to be a global max. You can do the same thing for your second derivative test. If it is only concave up, then it's a minimum global min, and if it's only concave down, then it's a global max. So this gives you a way to modify if you want to find some absolute extrema for the entire graph that you're looking at. Notice this is not on a closed interval, because on a closed interval you have to use EVT and check your endpoints. All right, here's your closed interval test for your absolute. Here are your guidelines, and then your last important, the extrema, the value, the max of the min is the y value, the location is the x. And that's going to summarize everything that we have for our applications of derivatives and using them to sketch the graphs. And so from this point on, you'll go ahead and you'll work on your worksheet for that. And we have the test that's coming up that's going to include basically chapter 3, which is your derivative rules, and chapter 4, all of these applications that had to do with graphing only.